be doing that. I.e., for many electron atom, we will just add the different angular momentums and the spin, and then add them together to basically obtain the same term symbols. We are still working on atoms. So as you can see here, angular momentum for many electrons still commute with the Hamiltonian. Yeah. So we have your L there, and then you have the LZ. This time, because there are many electrons, so the letters will be capital. So before this, because there's only one electron, the letters are all small letters. So the L and LZ, they still commute. They share the same Hamiltonian. They share the same wave function, and spin as well. Now it seems that for spin, the spin operator commutes with the Hamiltonian until the atom, until polyatomic atoms. So all labelings, even up to polyatomic molecules, you will still see spin states as part of the symbol, because spin operator commutes with the Hamiltonian operator of atoms and molecules as well. So there's no problem with spin, but there will be a problem later on with angular momentum. Yeah. So for many electron atom, they still commute with each other, so that is not really a big problem. We can still use angular momentum and spin symbols to label electronic states of atoms, of many electron atoms. Yeah. Okay. Before we go ahead, let's have a look at or have an idea of what is really going on when we talk about atoms. Yeah. So in school, or in school, in the university, we are given lectures on quantum mechanics, and we are. Hold on, let me pointer options. Okay. So we are used to this part and this part, yeah, because in the Hamiltonian, we know in the standard Hamiltonian, we have the kinetic energy T plus V, and for atoms we have V and E, i.e. the potential between the nucleus and the electrons, plus VEE, which are the potential between the electrons, what do you call that? Repulsion between the electrons. So this H constitutes T and V and E. Yeah, and I've mentioned earlier that V and E can be ignored because, sorry, not V and E cannot be ignored. But the T of N, yeah, you have T of N here. So originally it should be like this: TE plus TN plus VNE plus VEE. So because the nucleus is much bigger than the electron, so usually this is ignored. If it is not ignored, then you will have to use T mu, yeah, where mu is the reduced mass, but you can say that it's practically the electrons only. So this one is not there, so it's only just TE plus VNE. Yeah. So TE plus VNE, this part is inside here. Okay. And VEE is the one that is there. That one. Yeah. So you can see there's Rij, right? Rij is the distance between electrons I and electrons J. So the first part, you have T1, which is the unperturbed hydrogen-like Hamiltonian. So it's just the Hamiltonian that you get from, if you can solve it, you can't solve it, but if you were to be able to solve it, the T1, or the unperturbed hydrogen-like Hamiltonian, is the first part. The second part is associated with the electrostatic interaction of the electrons. So electrostatic interaction of the electron is this one. So this is T1, this is T2, and then you have your spin orbit coupling, which is here. So that is T3. Okay. So in the university, we learn mostly about T1 and T2 in quantum mechanics lectures, but rarely we go to T3 unless we're doing spectroscopy. Yeah. So the original Schrodinger equation will only give you T1 and T2. So if you want to get what you call that, the term symbol, you are only stuck at, let me do this, 2s plus 1 xj, right? So j is is associated with T3, and the whole thing besides the j is T1 and T2. Yeah. So usually when you see in books, what you see are symbols like this, 1s or 2p. Yeah. That means these symbols are symbols where spin orbit coupling is still not taken into account. So then only you will have spin orbit coupling. So you have 2p half or 2p3 over 2, etc., etc. Yeah. Right. So the three terms represent the levels of interaction and coupling. So when you solve the Schrodinger equation, you get T1 and T2. Then when you look at the spin orbit coupling, then you will get T3. Okay. So this is basically the same. If we were to do
Kali ini problem is connection. Kita tunggu sebentar ya. Ini Pak Syarifnya terpental dari Zoom. Kayaknya ada masalah koneksi. Oh, ya sekarang sudah ada lagi.
Saya dengar.
Sudah boleh lagi sekarang Prof.
Bentar ya, bentar. Apa?
Bu Yusi bisa dijadikan co-host Pak Syarif.
Ini saya sedang gunakan telepon nih.
Benar.
Bentar. Dengar?
Dengar.
Oke. Nanti saya sedang restart komputernya. Tapi saya bisa teruskan. Bentar ya.
Silakan.
Bentar. Ini gunakan telepon aja. Terus-terusan masalah ini. Bentar ya.
Nggak apa-apa, Prof.
Allahu Akbar. Bismillahirrahmanirrahim. Oke, bisa dilihat ya?
Boleh lihat.
Oke. Baik. Jadi kita lihat dahulu untuk T1 dan T2. Ini sementara itu saya itukan komputernya ya. Allahu Akbar. Bentar ya. Yang komputer ini lebih selesa lah. Teleponnya susah.
Iya.
Baik, kita lihat T1 dan T2 dahulu. Ya, jadi kita harus sum up. We have to sum up. Okay, before that, when we talk about many atoms, we will be talking about two types of calculation or determination. One is for different electrons or non-equivalent electrons. For example, if you talk about two electrons, one in another orbital and the other one is in another orbital, like for example 2p1, 3p1. So these are two totally different orbitals, or 2s1, 2p1. These are also two totally different orbitals, and these are known as non-equivalent electrons. But there are possibilities that we also have equivalent electrons, where two electrons are in the same orbital. Yeah, if they are in a p orbital, for example 2p2, so those two electrons are equivalent electrons. So determining the term states or term symbols for two different electrons is easier than determining two same electrons. So we have equivalent and non-equivalent electrons. We'll just forget about the equivalent electrons because determining it, you have to actually draw a table, and then you have to look at each and every microstate and then determine which microstate have the same energy. So it takes a longer time. So we'll just look at non-equivalent. This is for the sake of understanding the how to actually come up with term symbols conceptually. Okay, so we have two non-equivalent electrons like 2p1 and 3p1, for example. So what we have to do is we have to add the individual quantum numbers of each electron. For example, if we have 2s1, 2p1, that's easier to think about. So you have 2s1 and 2p1. So you have electron number 1, which is in 2s. L1 is equal to 0, right? For 2p1, this electron, L2 is equal to 1. Yeah. So then we add the electrons this way. Okay, L1 plus L2 until L1 minus L2. So for this state, for this configuration, the total L will be 1 plus 0 until 1 minus 0, which means it is only 1. L is only 1, which means the only state that can arise, the only term symbol that can arise is S. Okay, then we have to think about the spins later on. Yeah, but this is how you do it. What you have to do is you have to sum the orbital contributions of each electron in the non-equivalent orbitals. So this is an example of 2p1, 3p1. You have two electrons in two different orbitals. So it is L plus 1 to L1 plus 1 to 1 minus 1, which is going to be 2 to 0, which means in the middle there will be 1. So L will have the values 2, 1, 0. So the state that will arise out of this is S, P, and D states. S is where L equals to 0, L equals to 1, L equals to 2. Okay, so the letters are SPD terms, right? These terms differ on account of the different spatial distribution, okay, and the subsequent differences in repulsion between them. If there are 3 electrons, then you talk about L equals to L plus 1, L plus 2, L1 plus L2 plus L3 up to a certain rule, okay? So you couple the first two first, and then you couple after the result of the two, then you couple the third one. Something like this, hold on, something like this. So you have 3 electrons. Say for example, it's 2s1, 2p1, 3p1, for example. So you have L equals to, first you do this, so you have L1 plus L2 until L1 minus L2. Once you've got that, this is not L yet, sorry. This is not L yet, okay. This is just some L, say L, I don't know, L prime. And then you have L, which is going to be L prime plus L3 until L prime minus L3. Then you will get the total L, okay. So that's how you do it. And then you sum up the spin. Spin is, the summing up is like this. It is actually sum of all S, and then sum of all S minus 1, sum of all S minus 2, and so on, until S becomes 0. Whenever S becomes negative, then you stop, okay? For example, you have 2 electrons, so it's like S equals to half plus half. Remember, the spin quantum number is just half, half plus half. Then you have half plus half minus 1, half plus half minus 2. So this is already negative. So you only stick with the 2. So equals to 1 and 0. Okay. And the multiplicity of the term is just 2s plus 1. Now we're going to look at some examples later on. Okay. Right. Okay, this is a very important thing as well, because this is what will determine the quantum states of electrons and atoms. When the shells are filled, what we mean by shells are filled, so we have all these energy levels. Okay, you have 2 electrons pairing each other. So if all the shells are actually filled, i.e. everything is paired, right? The term that can arise is only the net L and S is equal to 0. So when we want to work out term symbols, we only need to consider electrons of the unfilled shell, because for L and S of filled shells, the net L and S will be equal to 0. So that is why when we have a big atom, for example, okay, with many electrons pairing up in the atomic orbitals, right? And you have the highest occupied orbital with 1 electron, you don't have to consider all this. You only consider the topmost, where you have unfilled or rather unpaired shells. So if you have, say, for example, 2 electrons at the topmost, one is in the P and one is in the D, then you only consider the 2 electrons which are not paired up in order to determine the electronic states. It's okay. We'll look at some examples. Right, these are some examples of filled shells. You have, say, for example, helium. So everything is basically zero. Yeah. So the only state that can arise is just 1s. So we for the others we don't really bother. We will just look at, in order to determine the most important state of a particular atom, we look at the unfilled subshells. Yeah. Okay. We'll look at that again later on. Don't worry. Right. T3 is where we actually do the angular momentum and spin angular momentum, the orbital angular momentum and the spin angular momentum coupling. Yeah. So we know of the L, we know of the S. Now we have to add the L and the S in order to get a J. Because we know the term symbols is in this form, 2s plus 1, say an X there, then you have J, right? X is determined by the value of L, and J here is basically L plus S in a vectorial way, L plus S, right? So how do we actually do this? Now, there are two ways of doing it, okay? Two ways of calculating J, right? Because J is basically the vectorial summation of L and S. One is called the Russell-Saunders coupling. Russell-Saunders coupling. Let me do this one first. Computer. Russell-Saunders coupling is usually for atoms of low atomic number. And the way we do it is that we calculate the total L first, and then we calculate the total S first, then we vectorially add L and S. Okay. So bold here because they are vectors, they are not simple L plus 1. Yeah. And the J operator also commutes with the Hamiltonian operator. Hence, you can get this equation here. Right. So we have for angular momentum, if you can still remember, it's L times L plus 1. Yeah. The value of actual L is equal to this. And for J, it is also equal to the same number. Yeah? J, hold on, this is the actual value of J. So the magnitude of it. Eh? So it's J is equals to J plus 1 square root. Right? Okay, so how do you do it? We just add the L and S. So we add L and S until L minus S. Say, for example, we have L equals to 3, S equals to 0. Yeah? Or S equals to 1. S equals to 1. Okay, one case. So J will equal to 3 plus 1 until 3 minus 1. So it's going to equal to 4, 3, 2. Yeah, because final one is 3 minus 1. So you will have L equals to 3, S equals to 1. For this one, L equals to 3 is actually F. Yeah, F. So we have F. S equals to 1. 2S plus 1 is equal to 3. And J, you will have 4, 3, 2. So you have three different term symbols: 3F4, 3F3, and 3F2 term symbols arising from electrons in which has a total value of L equals to 3, and spin is equal to 1, or it's a triplet multiplicity. Okay, so you get this terms. So in this case, a 3D term has a configuration of 2p1, 3p1. So you have to add the L and the S. Okay. So L equals to 2, S equals to 1, 2 plus 1 until 2 minus 1. So the values of J are 3, 2, 1. The permitted values of J are 3 to 1. And the terms that arise are 3D3, 3D2, and 3D1. Okay. Not very difficult. Okay. So you can actually work out any configuration as long as they are non-equivalent. Once they start to be equivalent, so it's not going to be as easy as you may think. Yeah, you have to actually look at all the different microstates. So these are all non-equivalent electrons. Yeah, like this D3 term, 2p1 and 3p1, right? Non-equivalent electrons. Okay, so the next type of coupling is known as the JJ coupling. JJ coupling is for large atoms, heavy atoms with high atomic number. Yeah? The spin orbit coupling is large. Now, in this case, you have to actually do a coupling of individual electrons. Yeah, to J, then you sum up the J. Yeah, so that's JJ coupling. So we are going to look at mostly the Russell-Saunders coupling because we are going to couple only small atoms. Yeah. Okay. So method 2 is better applied to a large atom, which is known as the JJ coupling. Right. So either we use the JJ coupling or the Russell-Saunders coupling. We're going to obtain the JLS, and then we can label the JLS based on this labeling. Actually, L is not very good. You have to put X, much easier, isn't it? Won't be confused because there's also L when symbol L, but you can actually use L. You can, yeah. So it's 2S plus 1 L J. So depends on the value of L. If it is 0, then you have a big S. If it is 1, you have a big L. If it is 2, you have a big D. Yeah. Then you have your multiplicity there and the actual spin orbit coupling quantum number J. So it's not very difficult, quite easy lah. So the most stable with the lowest energy arrangement, once you have the symbols, okay, it's spread out. Lowest energy arrangement of electron is to spread out the electron before pair up. So the lowest energy for a given electronic configuration is the one having the greatest multiplicity. So the when you have 3s, this is lower than 1s. Yeah, so it's lower in energy because there is it has the greatest multiplicity. If more than one state has the same multiplicity, then the lowest energy of this is that with the greatest L value. So the lowest energy is with the greatest L value. So you have yeah, that's right. So the greater L is, the lower is the energy. Okay, is that clear? Put this one out. Any questions?
Ada yang kurang jelas? Ada yang mau bertanya terkait dengan term simbol? Bisa dipahami ya?
Recording.
Sorry. Okay. Yeah, any questions?
Mulai paham.
No questions? Okay, actually this is what we've done is something which is it's not that difficult. I'm sure you have done this if you have done spectroscopy, I'm sure you have done this. So we are for an undergraduate standard, students are expected to be able to come up with the term symbols for atoms, for many electron atoms. Yeah? In fact, it's very important whenever you do research. For example, if you do laser research, and most lasers will in atoms, so you'll be playing with term symbols. Yeah, and each energy level will be labeled as using term symbols. So for small atoms, it's quite simple, but for bigger atoms, you will have a lot of term symbols, and you have to understand. But with the term symbols, you will be able to assign spectral lines. Yeah, that's the good thing about knowing how to do it and being able to identify which lines in the spectrum belongs to which transition. Okay, right. I think my my computer is ready. I'll just change it. Hold on. Let me log out from here.
Kalau ada pertanyaan silakan ditanya ya. Nah, tadi time symbol kali kita udah biasa ya.
Right. Okay.
Oke.
Ya. So harapnya komputer tuh tidak inilah.
Bu Yusi bisa minta tolong dijadikan host Pak Syarif.
Ya?
Oh iya ya.
Ya,
Bentar.
ya, oke.
Gimana, Pak?
Jadikan co-host untuk ini. Share screen.
Oh, gitu ya.
Oke.
Bentar ya. Oke, bisa nampak ya?
Sudah.
Oke, insyaallah. Baik. Langsung terus ke slide yang keberapa ini kan? Oke, diatomic molecules ya. So atom sudah. Atoms, the term symbols depend on the total angular momentum, the spin and total spin and total orbital angular momentum. So the energy levels are determined by labeling based on the term symbols, which are really term symbols associated with the angular momentum, the spin, and the spin orbit coupling. Yeah, so that's quite easy. Now, when we go to bigger systems like a diatomic molecule, then we begin to see problems. Of course, the problems has been solved. So the Hamiltonian still commutes, but it only commutes with the electronic angular momentum along the bond. Yeah, only along the bond. So the total angular momentum L is no longer commuting with the Hamiltonian. So we have to use a different set of term symbols in order to label the electronic energies of diatomic molecules. Yeah. So we resort to only looking at the angular momentum along the bond. Yeah, along the bond. So hold on. Right. So in linear molecules, the lack of spherical symmetry destroys this relationship. So it's no longer commuting. So it's not equal to 0 anymore. It is now equal to non-zero. So this is for atoms, but for molecule
belum ada di screen, Prof.
Oh, belum ada ya? Oh,
Belum share. Belum share.
Apa ya?
Belum share screen.
Share. Oke.
Oke. Sekarang udah muncul. Ada.
Oke. So saya ulang kembali lah. Right, for diatomics, the Hamiltonian still commutes, but it commutes only with the electronic angular momentum along the bond. Dengan kata lain, ya, ini adalah SL. Jadi SL, J dan JZ, ya, kita gunakan untuk characterize a particular state lah. JZ nggak perlu lah. Hanya S, L dan J untuk atom, ya. But when we go into molecules, linear molecules, we see that this relationship no longer holds. Yeah, this is for atoms. Right now, for diatomic molecule is not equal to 0. Yeah, so L no longer commutes, so we cannot use the total angular momentum. But we are lucky because the LZ still commutes. So LZ, gone. So we have Lz commuting with the Hamiltonian. So we can still use Lz as a way to label electronic states of diatomic molecules. So we will be working with a new set of operators. S, as I've mentioned earlier, S spin, it commutes with the Hamiltonian up to polyatomic molecules. So Sz also commutes. Lz, okay, and of course we will talking about Jz, which is equal to Sz plus Lz. Yeah, only the Z exists, yeah, which still commutes. So Z axis is defined as the internuclear axis of the molecule. Okay, so they will be used to describe the molecular states. Okay, so the different symbols are used. We have the total orbital angular momentum, yeah, but this time it's not the total orbital angular momentum as in atoms, but rather total orbital angular momentum around the internuclear axis. So the symbols will be different. Rather than using L1 and L2, so rather than using L1 and L2 for atoms, for electrons in the atoms, we use lambda 1 and lambda 2 for electrons in the molecular orbital. Yeah. So now we are going to be talking about molecular orbitals rather than the atomic orbitals, right? But because we are not going to bother about the kind of molecular orbitals that we get from diatomic molecules, because we can still use angular momentum along the nuclear axis as a way to label electronic states. So we're just going to use it straight away, and we don't have to think about how the molecular orbitals are formed from the atomic orbitals. So the state symbol, this is capital lambda. So you have capital lambda equals to 0, we will use sigma. Capital lambda equals to 1, we will use pi. Capital lambda equals to 2, we will use delta, and then 3, we will use phi. Yeah. Spin is the same, okay, because spin always commutes. So the way to do it is basically the same, right? And the multiplicity also stays the same for diatomic molecule, right? It's 2s plus 1. And we look at one example. So the simplest example is, of course, the hydrogen molecule. Okay, so we have the hydrogen molecule is formed by two 1s orbitals forming molecular orbital. The lower energy is the bonding orbital, right, which is symbolized as sigma. Okay, G, and the one on top, the molecular orbital, is symbolized as sigma U, right? Now again, the symbols for sigma G and sigma U, all these symbols come from the character table, yeah, because I think when we talk about a diatomic molecule AB, the symmetry is, I think, the D infinity H, right? D infinity H. Yeah? So the irreducible representations are given by sigma, if I'm not mistaken. Yeah. So we look at one example, the hydrogen molecule, where you have two electrons in the 1 sigma G molecular orbital, right? So again, we have two electrons, so we have S is equal to 1. So S cannot equals to 3 because you cannot get both electrons pointing up. The energy is just too much. So the multiplicity is only S equal to 0. The only way you can get a triple state is when you have two, say two orbitals, right? If there is a transition, then one pointing up, one pointing down, different energies, right? Then you can have S is either 1 or 0. This is equal to 0. So the other possibility is one pointing up, another one pointing up, different energies. And this is when the spin is equals to 1, the total spin. Right, all electrons are paired, so S is equal to 0. Multiplicity is always equal to 1. What about the Z component? So both electrons are in the sigma orbital, hence lambda 1 equals to 0, lambda 2 equals to 0, and the total lambda is equal to 0. And the symbol, as we've looked at before, when it is lambda, total lambda is equal to 0, the symbol will be sigma. Okay, so we will have sigma there. So what we will get is basically sigma we're gonna get is, so sigma, and this is S equal to 0 and multiplicity is equals to 1, so sigma 1. Okay, and then omega, which is the total orbital total angular momentum, which is analogous to J equals to L plus S. Yeah, so this is J omega equals to lambda plus S, which is the total spin, right? So lambda equals to 0. This is also equal to 0, right? Hence this is 0. So it is basically 0 there. Okay. For linear molecules, there is another symmetry consideration, which is the symmetry based on the inversion. Okay, so for hydrogen atom, what you have is, you have two hydrogen atoms like that. So the sigma G molecular orbital, if you look at the shape, it is basically like this, with the same charge all over the place, right? So there is actually a point of inversion there. So if you take any point there, you invert through this point, you reach there, the charge doesn't change. So this is positive, this is also positive. The fact that there is no change in charge, that means there is another symbol added to it, which is G, gerade, yeah, in German. So that means there is no change in charge when you undergo inversion from any point. Yeah? So this will be the term symbol, but usually people will ignore the 0 there. So what you'll get is just there, 1 sigma G. So you have an electronic state, which is another thing that needs to be clarified. Electronic state, which comes from the electronic configuration of 1 sigma G2. So 1 sigma G2 gives rise to a 1 sigma G electronic state. So an electronic state, this is very important, an electronic state is determined by the electronic configuration. That is why we have two symbols. One is sigma, which is capital sigma, and the other one is the small letter sigma. So you have big sigma to identify electronic state, and the small sigma to identify the orbital. Yeah. So the orbital has symmetry because the orbital will follow the symmetry of the molecule. And once you fill electrons in, it is how you fill the electrons that will give you the electronic state. Yeah. So state and electron configuration are basically the same thing. Electronic configuration equals the state of the molecule, in this case a diatomic molecule, right? So that's why in even in atomic spectroscopy as well, the state is given by the term symbols, that is the electronic state, and it is basically due to certain configuration. Yeah, but usually people will not think about the configuration. People will just talk about states, electronic state, in terms of term symbols. Yeah, for example, we talk about 1 sigma G, the capital 1 sigma G here is excited to another electronic state. But within that excitation, of course, there is a change in configuration. Yeah? So the other electronic state, the excited electronic state, will have a different configuration. Yeah, I mean, they will make more sense later on. Okay, so this is basically the summary of it, lah. So what you have is this is the term symbol. Okay, 2s plus 1. That's the multiplicity. Capital lambda is the sum of L1, lambda 1 plus lambda 2, etc. And then you have your omega there, yeah, which is the which is the sum of spin and angular momentum, and whether it's Gerada or Ungerada. Okay, this is due to inversion. Now this only exists in diatomic molecules, and there is a plus minus there, which is due to reflection. Okay, inversion and reflection. So for hydrogen atom, you have sigma G down there and sigma U up there. It is G because if you think of H and H, right, it's basically one lump. Okay, but for U, it will look like this. So this is the H and the H there. So this is positive, this is negative, right? So any inversion will give you Ungerada because the charge, sorry, not the charge, it changes from positive to negative or negative to positive depending on where it is being inverted, from where to where. Yeah? And plus minus is the exists in the middle of the bond, and basically it forms a plane, so you can actually reflect any point within the orbital through the plane going next to the other part of the atom, of the molecule, and see whether there is a change or no change in the charge, not the charge, whether it's positive or negative, yeah, the sign. Okay, right? So for heteronuclear diatomics, okay, so for an AB molecule, for example, the term symbol does not include the GU part, for there is no inversion center, right? Because A and B are two different things, but you can still go through the reflection one. Yeah? But inversion, by default, inversion means you have two same atoms on both sides, right? And there's an inversion point there in the middle. Okay, so for heteronuclear atoms, diatomics, it doesn't work. So there's no G or U for heteronuclear diatomics. Okay, right. Let's have a look at how this works out. Okay, if we look at a proper molecule like the oxygen molecule. Okay, so the oxygen molecule, the states that arise from this configuration, 2p pi u and 2p pi g, okay, right? The states that exist are these states. Yeah. So you have three triplet, sigma minus, which means there is change in sign when you do reflection. And then you have one delta G. Delta is for lambda that equals to 1. Yeah. And you have one sigma G plus. So these are the states that arise from the lowest electronic configuration. Yeah. You can try to work it out if you want to. So these are the states that arise from these configurations. Remember we talked about which one is the lowest energy out of the three. It will be the one that has the highest multiplicity. So you have a triplet state as the lowest energy. So that means the ground state of oxygen molecule is actually triplet state, okay, where the two electrons are pointing up in different orbitals, of course. Yeah. And which one is the next lowest energy? H will be where the angular momentum is lowest. Yeah, so is highest. So delta is higher than sigma. So delta will be the next one here. Because it is a singlet state, that means the two electrons are pairing up with each other in one orbital. Okay, and the third highest state is where the two electrons are pointing up and one pointing down, because it's a singlet state, right, which is the highest energy. Now, why do we represent each state as a curve like this? Now, of course, in chemistry, one of the most basic things that you will learn is when you have an AB molecule, B can be the same as A. We talk about A, B having or moving. They can vibrate like a simple harmonic. Yeah? So when you think of a simple harmonic motion, what you will see is, sorry, I can't draw this properly. Yeah? Okay, so in a simple harmonic motion, you would have a curve like this. Yeah, just a hyperbolic curve like this. Yeah. So A and B will just, if you think of it as vibrating like this, it goes back and forth, back and forth. So you can think of it as going up, down, up, down, up, down. Yeah, like a marble in this well. Yeah, but of course A and B can break, so you can't represent it as a simple harmonic motion. You will have to use this kind of curve like that. Yeah, because at a certain point A and B will break. Right, so there's a dissociation energy. Okay, so this is for one particular spring, because A and B can be thought of as springs, right? So each electronic state will have a different spring. There are different springs. So when they have different springs, they will have different potential energy curves. Yeah. So that's why for 3 sigma G, we will see that the curve looks like this. 1 delta G, the curve looks like that. 1 sigma G, the curve looks like this. Okay. They are basically different springs. So you can think of this as, let me do it again, 3 energy levels like that. This is 3 sigma G, this is 1 delta G, and this is 1 sigma G. So there are 3 energy levels like this. Each energy level can be represented by the curves. Yeah. So if you talk about this transition, right, from 3 sigma G to 1 delta G, this transition will involve a lot of possible rotational levels. Now we're going to look at this when we think about the Frank Condon principle later on. Yeah, but that's basically it. So we can represent the energy states like this as levels like this, or each level can be represented by a curve like this. Next one, these curves. Yeah. Now if you look at the next one, yes, right. So this is the curves for electronic states of oxygen molecule. Yeah, so we can think of it this way. So this is your, I'll just draw it. So we'll just draw the states like this. So we have one energy level there, and then somewhere here, there, another one, there, there. And we have another one there, which is there, and there is that one. So we can label them 3 sigma G, and this one is actually 1 delta G. The one above is 1 sigma G, and this one will be 3 sigma U plus, this one will be 3 sigma U minus, right? So you can have transitions, right? Of course, there are rules. For example, actually this transition is not allowed because you have triple going to singlet. So maybe you can see this transition, triplet to triplet, okay, sigma to sigma, okay, G to U. They are all rules, which I think is, yeah, there you go. So the selection rules are delta delta lambda can be 0 or plus minus 1. That means sigma can go to sigma, sigma can go to pi. Okay, no problem, because it can be plus minus 1. Spin, it has to be delta S mass equal to 0. So that means 1, 3, 3 sigma not allowed. But 1 sigma G to say 1 pi U, this is allowed. Yeah, because G must go to U, U must go to G. Yeah, so this transition is allowed. So if you look at the this one, so 3 sigma G can go to 3 sigma U. So this transition is allowed. This one is not allowed. This one is not allowed. Okay, this one is allowed. What about this? So you can get from here to here as well, right? Okay. So some transitions are allowed, some transitions are not allowed. We look at that later on. Okay. But basically, this is how it's done. So each state can be represented by a curve, because the AB molecule can vibrate, right? But they vibrate with different springs. Of course, when they are vibrating with different springs, the potential energy will be different. So that is why we represent for a diatomic molecule the energy or the electronic states as different curves having different energies, right? Okay, what else is there? There's a selection rule, huh? Okay, any questions before we go ahead with Frank Condon principle?
Ada pertanyaan? Tadi tentang stem simbol untuk molekul, di atomic molekul. Oke, boleh pahami semua?
Semua okay? Jadi, yeah, I mean, it's not you're understanding me, so there should be no problem, yeah. I am making sense. Okay, kalau begitu kita teruskan ke Frank Condon principle. Now we are still talking about diatomic molecule, and you know that the state of a diatomic molecule is represented by the electronic configuration, right? And the change in electronic configuration means that there is a change in bonding strength. Yeah, so the bonds can be represented by springs. I always like to think of it this way. So different electronic states will have different springs. Yeah, different springs. Now, different springs means that, of course, there will be some changes in terms of vibration when there is an electronic transition, because suddenly you change the spring. You get what I mean? Say, for example, you have a motorcycle spring as the ground state, AB, molecule AB, with a motorcycle spring. Okay. So you have molecule AB. So the ground state, you have AB sepeda motor, spring, sepeda motor. But suddenly there is an electronic transition. Now, electronic transition is really quick, very, very quick, yeah, compared to the motion of the nucleus. Yeah, electronic transitions very quick compared to the motion of the nucleus. Yeah, I always give examples to students this way. Kamu bisa nggak tahu atau pernah nggak tengok movie atau drama gitu ya, yang mana kita bisa tengok macam ada magic gitu. Jadi seseorang itu sedang dalam kamar tidur, pakaiannya pakaian kamar lah, pakai kamar tidur, pakai pijama ya misalnya. Tapi oleh kerana magic itu lebih cepat, dia bilang, oke, sekarangnya kamu ada di kamar tidur. Terus yang bikin magic itu karena sekarang ini kamu harus berada dalam kelas gitu. Jadi dalam keadaan berpakaian pijama itu, kamu terus ada di kelas. Paham nggak? Nah, karena lajunya magic itu berbanding dengan kebolehan manusia untuk bertukar pakaian. Karena of course pakaian pijama itu di dalam kelas itu kurang sesuai kan? Ya. Tapi pertukarannya begitu cepat sekali sehingga kamu belum sempat nukar baju. Ya. Sampai di kelas masih pakai pijama gitu ya. Nah, jadi sampai di kelas barulah nukar pijama pakai baju yang sesuai untuk kuliah gitu. Nah, karena manusia ini ngambil masa. Magic itu cepat saja. Nah, begitu juga dengan electronic excitation. Electronic excitation is so fast that the molecules cannot catch up. So the electronic transition is so fast that the molecule cannot catch up. Bayangkan ketika bertukar saja, ketika electronic transition occurs, the spring changes. Jadi bayangkan kalau kamu punya dua bola besi ya, sedang bergetar gitu, ya, dengan spring sepeda motor, tiba-tiba spring sepeda motor itu bertukar ke spring sepeda ya tidak bermotor, sepeda basikal ya. Tiba-tiba bertukar ke sepeda basikal. Jadi masih AB, tapi sekarang ini springnya spring basikal. Ya. Langsung, iya, artinya ketika berubah itu, the vibration suddenly it couldn't cope, isn't it? The vibration that naturally occurs in the ground state with the spring of a motorcycle, and suddenly the spring changes to bicycle spring. The vibration is not natural anymore. Okay, so when we talk about electronic transition, really we are talking about vertical transitions, right? Like this. So you have AB, which is there, and AB, another one, which is there. So the spring may be a bit different in terms of where is the equilibrium distance. Yeah? If this is R, this is the energy, V. So the equilibrium distance for the AB ground state, I just put a double prime there, and the AB excited state will be a bit different. But the transition will be a vertical transition. So you can imagine the energy levels from the solution of Schrödinger equation. So if initially the molecule is there at state V equals to 0, yeah, it will vertically be excited to state V equals to 1. Yeah. So from V equals 0, suddenly it goes to V equals 1. Di kamar tidur, tiba-tiba di kuliah. Gitu. Ya. Jadi V equals 0 to V equals to 1. Now this transition will be manifested in the spectrum. Okay, you will see differences in the spectrum, which gives you some information, i.e., you know that if the spectrum looks like this, the AB double prime and AB prime curves are the same, or it moves to the left, or it moves to the right. Okay, just from the spectrum, how the spectrum is manifested. Right. So basically, that constitutes the Frank-Condon principle. It says that because the electrons are so light, okay, electronic transitions are so fast compared to nuclear motion. The electronic motion is so fast compared to nuclear motion that the nuclear motion takes a while to adapt to the transition. Now, because it takes a while, and the spectrum that results from the Frank-Condon principle is manifested right in front of you, because you can see the spectrum, that means the spectrum is telling you how unprepared is AB prime, okay, when it is excited from AB double prime. Yeah. So how the spectrum looks like will tell you the unpreparedness of the excited state, right? So of course you can get a lot of information from this. You can get information about the energy levels in the ground or the excited state. Okay, so that is what Frank-Condon principle is all about. Right? Why is the hold on. Now there's something wrong with my mouse. Nothing works today. Okay, right. Next slide. So a transition between two different electronic states of a diatomic or polyatomic molecule, basically. To understand Frank Condon principle, of course, it's easier to look at the diatomic case because polyatomic case is multidimensional. Yeah? So you can only see the manifestation of the Frank Condon principle on the spectrum, but you can't really see or understand the spectrum based on potential surface, because the potential surface for polyatomic molecule is multidimensional. Yeah? It's a hypersurface rather than the potential surface, so you won't get a good picture if you want to try to understand Frank Condon principle based on the pictorial understanding. But for a diatomic molecule, yes, because there's only one changing variable, which is the R. Okay, so the transition between two different electronic states generally involves simultaneous changes in vibrational energy and rotational energy, and the change is basically seen as a vertical transition. Yeah? Okay, so in order to understand Frank Condon principle, we have to look at what's known as the Born-Oppenheimer approximation. Now, Born-Oppenheimer approximation simply says that the motions that occur in the molecule, okay, these different motions occur with different energies. Yeah. For example, if you talk about electronic motion, i.e., the motion of electrons in the molecule, the energy that you need in order to move electrons are very, very high. Okay, in the region of 10,000 to about 100,000 wave numbers, right? 10,000 to 100,000 cm-1. Whereas if you want to look at the vibrational motion of the molecule itself, okay, the energy required is about from 1,000 to 10,000, 1,000 to about 10,000 wave numbers. Okay? Whereas motion involving rotation of the molecule only requires energy from 1 to 10 wave numbers. Okay, so very small. So the difference in energies indicates that these three motions can be separated. I mean, you can treat them as independent of each other. So electronic motion is independent of vibrational motion, is independent of rotational motion. Okay, so because they are independent, then you can do this. Okay, so the E total of the energy is equal to E electronic plus E vibration plus E rotation. So the fact that you can add them up is due to the fact that they are of different energy domains. Yeah. So the difference in energy is very, very big. So this can be seen in this diagram. Yeah. So for the electronic energy, you can see the energy levels are represented by the curves. See, curves. So this is the diatomic curve. Okay. So whenever there is an electronic transition, you're talking about the transition from this curve to that curve, right? So if you think of the lowest energy, okay, which is there, V equals to 0, it's a transition from V equals to 0 to V equals to 0 up there. This transition is the electronic transition. Yeah. So usually this is called the origin, where you're talking about V equals 0 going to V equals 0. Now this happens because the potential above and potential below has very similar R equilibrium. Yeah, very similar. It's about there. Yeah, very similar R equilibrium. So you can see a V equals 0 to V equals 0 transition. Now the rotational levels are actually within the profile of the electronic state. So you can see different energy levels like that, different vibrational energy levels. So V equals 0, V equals 1, V equals 2, V equals 3, 4, and V equals 5 up there. Now the excited state will also have its associated V's up here. Yeah. So usually we will use conventionally, if this is both the same state, right? So I will say that I will label the ground as S1, up there, sorry, ground is S0, and up there as S1. So the electronic transition is involving S0 to S1. But S0 to S1 can also involve from V equals V double prime, which is the ground, equals something, going to V prime equals something. Okay. Sorry, hold on. Forget about this. It's like this. S0 at V double prime equals, say, 0. This one goes to S1, V prime equals 0. You can also have S0, V double prime equals 0, going to S1, V prime equals 1, and so on. Yeah. So all the series are actually electronic transitions, but involves different vibrational levels, in the excited state. Yeah. That's because the vibrational level exists within the profile of the electronic state. Now, for each vibrational level, there are rotational levels. So you have many rotational levels here, many rotational levels there, and there, and there. Yeah. But we're not going to talk about rotation. We'll just talk about vibration and electronic. Yeah. Okay. This is what I've explained. This is a better picture of the Frank-Condon principle. So you have two electronic states. One is the ground state, and the other one is the excited state, right? Now, because the excited state and the the ground and the excited state can have totally different curves, potential curves, and it can shift. You can see here, the RE for the ground state is actually somewhere. Hold on. So the RE is somewhere there for the ground state, equilibrium distance. And for the excited state, it's actually somewhere there. RE prime, this is RE double prime. Yeah. But because electrons move very fast, so any transition from the electronic ground state to the excited state is a vertical transition going up straight here. So you see that if you have a V equal to 0 there, V double prime, this V prime is probably equals to, I don't know, 6. Yeah. And this will reflect on the spectrum that you see, which we will look at later on. Yeah. Right. So then, why does the spectrum look differently if the potential energy surface between the excited and the ground state are different or they are similar? What gives the spectrum, the thing that, the characteristics that enables you to identify the equilibrium distance of the ground and electronically excited state potential curves, right? Is actually the overlap between the wave function. Yeah? So the ground state wave function, in this case, overlaps highly with the wave function at V double prime. V prime equals to, I don't know, 4 or 5. Yeah. So V equals to 0. It's not changing. Sorry. Keeps changing. the configuration for this should always be pen. So this is V double prime equals 0, and maybe this is V prime equals 5 or something like that. Yeah. But you see, there's a strong overlap. Now, this strong overlap will give you a very high intensity in the spectrum. Okay. So the movement, if you can think of the electronic excited state, can move to the left or to the right. Yeah. So if you were able to move the excited electronic state to the left or to the right, it will reflect on the spectrum, and this can be seen here. There you go. Yeah. So if the both the ground and the excited states have similar RE or equilibrium distance, the curves have similar equilibrium distance, then V double prime will be going to V prime, V equals 0. Yeah? So V double prime equals 0 will go to V prime equals to 0, right? And there will be a strong overlap between those two. Yeah? And what you will see is a progression, because it can go, this one, represents 0, 0. This one represents 0, 1. This one represents 0, 2. Yeah. Although the labels here are the other way around, because that is the way they write it. So if this is 0, 0, this is 0, 1, this is 0, 2. So 0, 0 is here, strong overlap, so high intensity. But 0 to 1 up here, the overlap is less. If you look at here, the overlap is a bit less, so the intensity is less. Until you go up to 0, 2, yeah, or 0, 3, yeah, 0, 3, the overlap between the wave function at 0 in the ground state and wave function at 3 in the excited state is very much less. So you will see that it is small intensity. So if RE for both excited and ground state is the same or almost the same, then you will see a spectrum that looks like this. There, yeah. But if the excited state is a bit to the right, okay, you will see that 0, 0 transition will have small overlap. But 0, 2 transition will have high overlap. So you will see the spectrum which is looking like this. So less, going more, higher, and then going down again, the intensity. Yeah. Now, if the excited excited state curve is very, very to the right, I mean, it's really going to the right, it's really far away. You see from 0, 0, there is some, or from 0, 4, there's a high transition. 0, 5, high transition. 0, 6, high transition because of the overlap. But then it can also go beyond the dissociation energy. So this is the dissociation energy, right? That means when the molecule, which is initially A, B double prime, this is A, B prime, but because of the progression, it goes up and up and up until it goes beyond DO for the excited state, and suddenly you will see a continuum. There is a, that means the molecule has well, basically broken. Yeah? So if you give high energy, you expose the system to higher energy, beyond a certain point, the molecule will just break because it goes beyond the bonding, yeah? The dissociation energy. So you have this kind of spectrum, right? Now the key point is here. For a diatomic molecule, or even for a polyatomic molecule, when you run a spectrum, you will probably see progressions like this. Yeah, progressions like this. So it goes from 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, right? And at 0, 3, you see that there is a maximum intensity, which means for this molecule, it is in this case where the RE for excited state is a bit higher than RE for the ground state. Yeah, R equilibrium of the excited state, yeah, is a bit higher than the R equilibrium for the ground state. So you will see a curve of intensity going up and then going down again, like this, going up and going down again. Yeah. So these peaks, they are called progression, and this progression gives you some idea about the energy levels in the excited state, because it gives basically, practically, it gives you the vibrational energy levels of the excited state, right? Because 0 stays the same, yeah. You know 0, 0, right? And then suddenly you also know 0, 1. So you just minus 0, 1 to 0, 0, and you will get the difference between the two energy levels, right? So a diatomic spectrum, electronic diatomic spectrum taken in a, say for example in gas, will give you the energy levels or the electronic structure of the excited state, because you can see the progression very well. Okay. Yeah. So it's the same thing here. For different molecules, you see, for example, oxygen, the Re prime is almost equal to the R double prime. That means you will see a spectrum like this. Okay. But for carbon monoxide, is Re prime is more than Re double prime. Yeah. So this one is almost similar, the two almost similar. For carbon monoxide, it looks like this. And for iodine, for example, it will look like this because the excited state is Re prime is much bigger than Re double prime. Okay, so you will see a continuum like this. So for each diatomic molecule, you can actually see the progression. You can calculate the excited electronic structure, and you can tell whether the molecule has Re, which is lower in the ground state or higher in the ground state compared to the excited state. So one example is this one. Can you see there? So you can see the progression. You can see the progression here. Okay, but this one, of course, is for SO2, so it's not a diatomic molecule. Okay, but you can still look at the progression. You can still calculate the excited state energy levels based on the progression. All right, any questions?
Ada pertanyaan? Ini semakin makin jelas ini ya, spektranya. Ada pertanyaan? Bisa dipahami? Boleh dipahami? Atau tidak paham sama sekali?
Nah, kalau perlu paham bisa, kalau malu mau tanya soalan sekarang, nantilah kemudian insya Allah diantar tuh message pada saya atau gimana? Ya. Okay, now let's have a look at something which is something that all of us will usually do. Okay, karena kebanyakan dari spektra yang kita ambil adalah spektra polyatomic molecule. Ya. Diatomic atoms itu mungkin research yang lebih khusus lah. Ya. Tapi kebanyakan research involves polyatomic molecules. So I'm just going to tell you or explain to you some of the basic concepts that you need to understand in order to appreciate electronic spectroscopy better, especially for polyatomic molecules. Yeah. Right, for polyatomic molecules or molecules more than 3 atoms, the labeling of the state is not the same as diatomic molecules. Yeah. Because for bigger molecules, the orbital angular momentum along the bond or whatever, it no longer commutes. Orbital angular momentum in whatever form no longer commutes with the Hamiltonian operator. Spin still commutes, yes, no problem. But we are lucky because for large molecules, usually we work with large molecules based on symmetry. Ya, sebab itu saya selalu bilang sama student saya, pemahaman yang jelas, yang baik mengenai group theory itu sangat penting dalam kimia. Walaupun saya tahu group theory ini ya, itu perkataan yang saya gunakan sebelumnya, leceh ya, rumit gitu. Dia tidak susah, tetapi rumit. Ya, terlalu banyak perkara yang harus kita teliti. Ya. Jadi ramai student yang sort of just leave it, but it's very important, especially in understanding molecules. Now, especially in spectroscopy. Okay. Now we are lucky because the symmetry operator, what you see in the character table, you see operators, right? These are operators. You have the I'll show you the table. Hold on. Let's see the character table. Okay, this is a character table for C2V molecule. Okay, so these are the operators: E, C2, sigma V, YZ. These are the operators, and these are the irreducible representation of a C2V molecule. Irreducible representation, right? And the one above is the symmetry operators. Now it turns out that the symmetry operator, okay, it commutes with the Hamiltonian operator. Now because of this, you can use molecular symmetry labels to label electronic states and molecular orbitals as well. So that is why for molecular orbitals, you see in a lot of chemistry textbooks, quantum mechanics or spectroscopy, you see small letters being used. Yeah? T to G, E, G. These are all symmetry symbols, symmetry irreducible representation symbols. If it is small letter, that means you're talking about the molecular orbitals. If it is capital letter, that means we're talking about the state. And remember what I told you earlier, the electronic state of a molecule is dependent upon the electronic configuration, i.e. how these electrons fill in the molecular orbitals, which are labeled in small letters. Okay, so electronic states depends on electronic configuration of molecules. Okay, right. So we use symmetry, to label molecular orbitals and electronic states. Okay, let's go straight into it. We're not going to do any group theory or anything like that, and I'm just going to give you a qualitative understanding. There are a lot of formulas in group theory, but I think the most important thing that you have to have in order to understand group theory is some common sense. Okay, now what do I mean by this? Now, if you take a ball, a ball is a very symmetric object, highly symmetric. It doesn't matter where you turn, right, or put axis anywhere you want, it's the same object. Yeah, you turn in any, or you do any operations on the ball, it's going to be the same ball, right? Anywhere you look at it, same ball. So ball is highly symmetric, right? Sphere, highly symmetric. But as you go into other shapes, now we are very lucky as human beings, because Allah subhanahu wa ta'ala has made molecules to have symmetry. Yeah. So for example, the simplest molecule like H2O molecule. H2O molecule is not a very symmetric molecule compared to a ball. Yeah. So if you can think of a diatomic, H2O molecule, this is an H2O molecule. Can you see that? Yeah. Something like this, the shape, right? So this is the hydrogen, and this is oxygen there. Now, if you were to rotate this 180 degrees like this, then it returns back to its shape, right? This is the original one. 180 degrees, it goes back to its original shape, right? That means for water molecule, a 180 degrees turn will return the water molecule to its original shape, correct? Right. Now that is an operation. Yeah. So what is the operation? Turn it 180 degrees, it goes back to its original state. So an operation in the character table basically does this. It returns the shape of the molecule or the structure of the molecule back to its original position, the way it looks originally. Yeah. So each operator does that. So as the molecules get more and more less symmetrical, right, you will see that there will be less and less operations, right, that will return it back to its original shape. If you talk about, say, for example, an object that has no symmetry, that means there is no operation that will give it back to its original shape, except it is not moving. Yeah. So there's only one operator, which is what? Anybody? For a shape, for a stone, for example, a rock, batu, ya, itu tidak ada simetri. Artinya hanya ada satu operator sahaja yang akan return the shape to its original position, which is what? What operator? It's not moving at all, isn't it? That is the operator. The operator is jangan gerakkan. jangan dikacau itu operatornya. Ya. Nah, gitu. Jadi untuk water molecule begitu. Ada beberapa operator yang sekiranya dijalankan ke atas water molecule, it will return to its original shape. Namely, not moving it, number one. Number two, rotating it 180 degrees. Number three, you put a mirror like this, a mirror there, and the reflection, and a mirror right through the axis, and it reflects. So there are only 4 operators that can be applied to water molecule to make it stay there at its position. Nah, gitu. Ya. Jadi persoalannya sekarang, for these operators, because each molecule there will be associated with the molecule certain things, like for example the molecular orbital. Yeah. So associated with a water molecule is the molecular orbital. Yeah. And the molecular orbital will also have certain symmetry. And we can use these symmetries as what's known as the basis function. Yeah. Or the basis for you to do the operation. And when you use this basis to do the operation, you will get certain numbers. And these numbers are different for different bases, which gives you the different irreducible representation. Gitu. So the different irreducible representation is based on the different bases. Right. Let's have a look at the ini saya bilang tadi saya tidak mau mengajar apa group apa symmetry group ya. Tapi ini terpaksa Karena ini is very important to understand this. Right. So there are 1, 2, 3, 4 operators, right? For C2V. Can you see? Only 4 operators that will return the molecule into its original position, which is not moving at all. This is C2 rotation 180 degrees. This is the vertical mirror, I think, and this is the horizontal mirror. Yeah. Now you have A1, where the basis of A1 is your z-axis. So if you just put a z-axis on the water molecule and do all the operations, you will see that each operation will give you a 1, 1, 1, 1. Yeah. 1 here means nothing. It doesn't change. It doesn't change. How do I say it? The axis doesn't change to negative, right? So let's look at this. So you have a water molecule. So this is X, Y, Z, right? Right. So if this is Z-axis, this is your Y-axis, this is your X-axis, and you put your water molecule to be like this. Oxygen there, hydrogen, okay. And you use the Z-axis as the basis, and you do the operation, not moving at all. So Z doesn't change, right? It doesn't change at all. It doesn't change at all. So for E, it doesn't change. So that means 1. There is no change in sign at all. C2, so you rotate the molecule 180 degrees along the Z-axis, right? It doesn't change at all. So it's 1. You do a mirror, so you reflect on the XZ plane. You know, this is the X and this is the Z. So you can imagine there's a mirror cutting through the H2O. The sign doesn't change as well. So it's 1 as well. And YZ is there. So it's in the middle. So it's reflection like this. Also doesn't change any sign in terms of the Z. Okay. So that means if you use the Z-axis as the basis, there is no change in sign at all. It's all 1, 1, 1, 1. And using a Z basis, you are going to get this irreducible representation. Yeah? But if you were to use, say, for example, the Y-axis, you will see, you can try it at home. If this is the Y-axis, this is the Y-axis. Remember, the molecule is still there, like that, right? And if you were to do a reflection on the XY axis, actually, this is the other way around. So this should be X and this should be Z, Y. Yeah, X. There should be. Hold on. Yeah. Okay. So if you were to do the same thing, don't move. Of course, nothing changes. Nothing changes. But if you were to rotate 180 degrees, okay, around the Y-axis, so this is the Y-axis, you rotate 180 degrees, you will see that the Y changes to negative. Yeah, it changes to negative, so it goes like this. It goes like this. Yeah, hold on. Yeah, it goes down. Yeah. So the sign changes, so it becomes negative. Yeah. Actually, the labeling of the axis, my axis is wrong. Yeah? But if you were to do it for y and for x axis, and then for the different other bases, x, y, y, z, this is for the d orbital. Yeah, you will see that each and every different d orbital will give you a different representation, right? So these are the bases used to do the operations to come up with the irreducible representation. Because you can't run away from this. You will have molecular orbitals with different shapes and signs, okay? And if you were to put these molecules, overlap them with the actual molecule, do the operation, you will see that there will be changes in signs, okay, for the different bases. So this is what we do in group theory, yeah? And this is very important because you will see that the different symmetries will cause different things to happen in spectroscopy. Yeah? We will look at that later on. Let's go back to the this one. Right. So for H2O molecule, there the different molecular orbitals. Everybody knows that molecular orbitals are basically linear combination of atomic orbitals. Yeah. So linear combination LCAO of atomic orbitals. Yeah? So it's a sum of all the atomic orbitals. So you can actually work out the symmetries of the different molecular orbitals, yeah, using the character table. So you form the molecular orbitals and then use the character table, run through all the operations, and for each molecular orbital, you can work out what are the irreducible representation. So for the first lowest energy of H2O MO, so we call this MO1, the lowest energy. The symmetry is actually 1A1. Yeah. So if you look at the C2V character table, you will see the A1 representation. Yeah. So 1A1, which means if you were to do all the operations on this molecular orbital, nothing will change. No change of signs at all. No change of signs at all. Yeah. So it belongs to the A1 irreducible representation. Now you go for the next one, yeah, which is this one. You do the same thing, do all the operations. You will also see that that MO is also belonging to the A1 irreducible representation. Now, of course, there are many molecular orbitals. There are as many molecular orbitals as there are atomic orbitals. So if you're talking about one particular molecular orbital is a sum of like 10 atomic orbitals, then there will be 10 molecular orbitals, each being summed up differently. Okay. So these are the energy levels of water molecules. So you can think of it as energy levels, lah. Energy levels. There you go. Energy levels. Yeah. Right. So we can then fill in electrons, isn't it? Depending on how many electrons there are for hydrogen, for water molecule, there are 10 atoms. Yeah, 8 in the oxygen, 2 from the hydrogen. So you have 4, 5, 6, 7, 8, 9, 10. Right. So this is the HOMO. This is the LUMO. Right. This is in general, but in reality, depending on the structure of the bent C2V molecule, like water molecule, it is bent at what, 108, 109 degrees, right? The bend between the two water molecules, yeah. So that bending causes some changes to the energy level, yeah. So the real one looks like this. There you go. So of course there is there's one down here, which is the 1A1. There are 2 electrons there, yeah, but it's not shown here. So you have 2A1 there, 1B2, 3A1, 1B1. So this is the electronic state of, sorry, the electronic configuration of water molecule. 1A1, 2, 2A1, 2, 1B2, 2, 3A1, 2, 1B1, 2, and finally, that's it. Yeah, 4, 10. Yes. So this is the electronic configuration of the H2 molecule, right? Okay. So H2O molecule in the ground state, right? Number of electrons 8, but actually there's another 2, right? The ground state. So you have 2A1, 1B2, 3A1, 1B1, all filled states. Now remember I told you that if everything is filled, then basically there is no, the net result is everything is 0, right? Yeah? Everything is 0, which means that the ground electronic state, will be the state where everything is symmetrical. This is how it translates to into the symmetry. So if all of them are paired like this, that means the state that you have is this state, 1A1. A1 comes from the character table, which is totally symmetric. Yeah, where everything is 1, 1, 1, 1, 1, 1. And the 1 there is the multiplicity, because everything is paired up. So 2s plus 1 equals to 1. So the symbol for the ground state of water molecule is 1A1. Yeah. So of course, if water molecule is excited, then maybe the electron from the B12 orbital will go somewhere else, right? There will be some changes in the electronic structure from the or the electronic configuration, and you will see a different electronic state. Yeah. Okay, actually it's already 11:55, so I'm going to show you something. Because kalau tak habis ni bisa kita buat dalam setengah jam selepas ini, atau mau teruskan gimana Pak?
Ya, teruskan aja Pak.
Teruskan aja ya?
Teruskan aja.
Okay. Kita tidak berehat langsung ya. Okey, nggak apa-apa. Kalau begitu, is everybody okay with this? Yeah. It's a bit difficult to swallow. I understand, you know, but I'm trying to give you the most qualitative, basic explanation about why or how these symbols come about. Yeah. So for polyatomic molecules, the term symbols, which indicates the electronic state, okay, comes from the electronic configuration. Now, some electronic configuration are fully filled. When everything is filled, that means symmetrically it is totally symmetric. So it has to be A1, right? And because it is singlet in this case, so it's 1A1, right? So the symbols will depend on the group character of the molecule itself. Okay. Now it is easier to understand this if you look at metal complexes. Yeah, metal complexes. So usually metal complexes, when we talk about I do not know what is it, the crystal field theory again. So in the crystal field theory, you imagine an ion in the middle, and ligands approach that ion in many different directions. Yeah, so you can have either a tetrahedral direction, you can have a planar. The ligands approach in a planar manner, or the ligands can approach in an octahedral manner. Yeah, so this different approach will cause the free ion term to split into different symmetry symbols. Yeah, remember, free ion is atom, right? So we are using the term symbols for atoms, but when ligands approach it, that term symbol is no longer an atomic term symbol. It has been broken. It becomes symmetry symbols, because now you're talking about, you know, molecules rather than atoms. So for example, if the free ion is D0 or D10, which means it is, you know, all are filled, everything is filled, so the free ion term will always be 1s. Yeah. And you also have D1, D9. For example, there's one electron, unpaired electron there. So it becomes D2D. It's a doublet state, right? If it is D5, then there are many different terms. Yeah. So transition metal ions with configuration D2 to D8 have more than one free ion term. So many different ion terms. Yeah. Right. So we have how the splitting is done, and we only look at the octahedral complex. If the term is S, right, which means, say, for example, D10, a D10 ion, right, is 1S, then the number of states is 1. There's only one state. So when the ligands approach in an octahedral manner, the only state that arises is A1G, totally symmetric. Okay. But if you're talking about atomic term, G, for example, and in G, there are 9 different terms, 9 different states, right? You have 2G, you have 3G, you have 1G and 3G, and many different J's as well. Yeah. So you have 9 different states. And this will break when it comes to octahedral into the different symmetry symbols. Yeah. So free ion terms split depending upon the symmetry of the complex. So you have octahedral is broken into these symmetries, but if you're talking about planar, they are broken into different symmetries. Yeah. Example, this one. Yeah. So you have the correlation diagram. Yeah. For example, you talk about 3F here, 3F for free ion, but when there is a weak interaction, it is broken into 3Ag. I think this is for tetra. So this is for octahedral, I think. Yeah. So it's broken into these 3 different term symbols. Yeah, symmetry symbols. But if there's a strong interaction, then T1G will go down there, 3T2G will go up here, and 3A2G will go up there. Yeah, right. So again, there's this Tanabe-Sugano diagram, which basically tells you almost the same thing. Yeah. So if it's 1S, it will when it becomes a molecule complex, it can only result in 1A1. But if G, there are a few term symbols, 1, 2, 3, 4. Yeah. So G1, 1G here breaks into 4 different symmetry symbols. Yeah. So this is something that all of us have learned before. So the symbols here are symmetry symbols, electronic states, remember? And these are the electronic term symbols for atoms before the ligands approach the ion. Right? So I hope that gives you some idea of our symmetry symbols. Yeah, we'll be using it in a bit. Yeah? Okay, that's done. So I ask another question because we are just looking at labels, right? So I'm going to ask this question: what happens when energy is absorbed, okay, or when the molecule is excited? What really happens? So in order to do this, we have to do a bit of quantum mechanics. Yeah. So we consider 2-level system, psi m and psi n. So we can talk about m level and n there. So this is psi m, this is psi n, and we're talking about a transition from m to n, right? So we're talking about electronic states. Huh? So we're talking about this as being electronic configuration 1, and here being electronic configuration 2, because we're talking about molecular spectroscopy, electronic molecular spectroscopy. So EC1 gives you the psi m state, EC2 gives you the psi n state, right? So this transition can be best explained if we use time-dependent Schrödinger equation and we solve it. So it's quite complicated. You can just open up any advanced spectroscopy book, you can find this, and in there they will derive something. And in the derivation is a long mathematical function. Within the long mathematical function is this term. Yeah. Now this is known as the transition dipole moment, R and M. So in different books they use different things. There are some books that use mu and m, for example, yeah, and a few other terms. Yeah. But this term, okay, may be used differently, but the transition integral is going to be the same. Yeah, it's psi n star, this is the complex conjugate. If it is a complex function, then you have to make this to a conjugate, and then mu and then psi. Okay, mu is the dipole moment operator. Now, dipole moment operator is just an axis, because electronic motion, it moves based on the axis, right? So from one point to another point within the same axis. Yeah. So the operator can either be x, just y, or just z, right? So if you're talking about a three-dimensional system, then you're talking about the possibility of the electrons moving along three different axes, x, y, and z, right? And usually they will break it up, lah. They will break it up into x, y, and z. But we'll see later on that you don't have to break it up. You can make certain assumptions, because we'll be doing some symmetry manipulation in order to see what is the value of R and M, right? So this operator is just an X or a Y or a Z, right? Now, mathematically, in order to do this, you have to do this one first. So this operator will operate on this wave function, the result of which will be multiplied with this wave function, and then you integrate the whole thing. Okay, but we're not going to go into the maths. We're going to use symmetry to actually work our way out. But if you want to calculate it, then you have to actually evaluate the whole integral, which usually is done using a computer lah. You don't bother calculating it on pen and paper. Yeah. So this R here, it forms the gross selection rule. You all know this, I presume. And it forms the basis of the various selection rules in spectroscopy. Okay. So the key is this: if R equals to 0, then there is no transition. If R is non-zero, then there is some form of transition. And the value of how much transition actually occurs, we can know if we evaluate the integral mathematically. Yeah, but it is sufficient to say that if it is 0, no transition. If it is non-zero, there is transition. That's the most, the grossest, the most basic rule. R0, no transition. R non-zero, there is transition. Okay, right? Because this is what we're going to do later on. We are going to use the symmetry of the integral in order to come up with the point that R, is it 0 or is it non-zero? Is R 0 or non-zero? We're going to use symmetry for this. And the rules are determined by the direct product of the symmetry representations of the states within the integral. Yeah. Is it my fault? Hold on. Right, I'll show you what it means. What is a totally symmetric representation? Okay, there are. I've given you two notes actually, details of electronic spectroscopy, and the other one is the normal electronic spectroscopy, which is there, molecular electron spectroscopy. So I don't think we have the time to actually go through everything, but I will go through one of the things, which is the selection rules. Okay. So if we look at the electronic spectroscopy notes, this note basically tells you about the selection rules of spectroscopic transitions. I've mentioned earlier that, hold on, use this, okay, that R and M is equal to psi n star mu psi m d tau, right? Now remember Born-Oppenheimer approximation. The Born-Oppenheimer approximation says that the total wave function for any molecular transitions, be it electronic or vibration or rotation can be represented as the product. Remember, E total is E electronic plus E vibration plus E rotation. Yeah. For psi, it's actually psi E, psi V, psi R. Yeah. It's just a multiplication. Okay. So we can actually break this down into the different types of motion. Yeah. So we can say that R and M is equal to, we'll just break it, ignore the star, yeah, ignore the star, assume that it's not a complex function. So we have psi n E times psi n V times psi n R mu psi m E psi m V psi m R. Right? So we just expanding the psi t that we are using here. Yeah. Now the mu can also be broken into mu for the nuclear motion plus mu for the electronic motion. So if we do the same thing again, and E psi n V psi n R psi m E psi m V psi m R. Okay, this is what we're going to get. So now I'm going to ignore something. I'm going to ignore the R. So I'm not going to think about the rotation at all. I'll just think in terms of electronic and vibrational motion, right? So this, if I were to do this, I can actually factorize this, and the factorization looks like this. Hold on, let me psi n E psi V or n V mu. Oh, we've done that. I'll break this one up. Sorry. We've done that. Break this up. This will equal to psi n E psi n V mu n psi m E psi m V, okay, plus psi n E psi n V mu E psi m E psi m V. In quantum mechanics, you just have to bear, just follow through. Now, what we're going to get is this, basically. Yeah, this will equal to psi integral n E psi m E d tau for E times integral of psi n V mu n psi m V plus psi n V psi m V d tau n plus, okay, plus, not plus, sorry, plus is actually multiplication of psi E n E mu E psi m E d tau. Okay. Right. Now, according to quantum mechanics, this will be 0 because we're talking about the orthogonality of two electronic states. Okay. So this will equal to 0. Hence, the whole thing will be 0. So everything will be 0. So what's left is of the R and M is this, basically. Yeah. So this part here, this is a very important part. This part here tells you about the Frank-Condon principle. Remember, I told you that what basically constitutes the Frank-Condon principle is you overlap between the ground and the electronic state, right? So this measures the overlap. It's an integral between the excited vibrational level and the ground vibrational level. Yeah. So this is your V prime. This is your V double prime. So this one is not orthogonal. Yeah. In fact, this is the overlap integral. So this is finite, so it's not zero, which leaves us with this. This is your electronic selection rule. Yeah? The electronic selection rule is where the electron, the excited electronic state, okay, psi Ne is multiplied by the operation of this over the ground electronic state, okay, and everything else is integrated. In other words, what we're left with is R and M is equal to this psi N E. Okay, you put a star back because that's the conjugate, mu E psi M E d tau. Okay, so after this, the symmetry considerations will be based on this, right? Okay, so if we go through with the notes, right, we see that there are a few spin, there's orbital selection rule, and another one is the vibronic selection rule. There will be too many. You can just read the notes. Yeah? But what we're going to do here is we're going to find a way to evaluate R and M. Yeah. So in order to evaluate R and M, what we have to do is we have to actually take the symmetry of psi and E, and symmetry of mu E, and the symmetry of psi and E, multiply them together, do a direct product, and if the direct product has in it a totally symmetric representation A, then R is actually non-zero. But if there are no totally symmetric representation, that means R is equal to 0. Yeah. For example, let's have a look at one example. For water molecule, I think it's in the notes. Okay, this is the water molecule. Okay, so you see, you can actually, these are the different electronic states of water molecule. Yeah. So the first one is 1A1, so you can draw it. The ground state is 1A1. I just draw it here. Okay, so this is 1A1. There's the ground state. The next state is this 1B1. 1B1. So this transition. Okay. So we can ask, what is this transition allowed? Is it allowed? Okay. So in order to do that, we say, what is R? In order to do that, we have to do this. So we have A1, a direct product with this, and a direct product with B1. What is the result? So what is this going to be? What's inside here? You will look at, because I told you just now that the that dipole moment operator is either X, Y, or Z, right? So it's either X, Y, or Z. Now X, Y, or Z, what are the representation? Is B2, B1, and A1, right? B2, B1, and A1. So we go back and we have to put here, what is it? B2, A1, and B1. Okay, so we multiply all this. What's inside here? We start with A1 times B2. This is B2, right? B2. A1 times B2 times B1. Okay, let's have a look. Let's have a look at the multiplication. Down here is the multiplication table. We are going to multiply A1 times B2 times B1. So A1 times B2 is B2. B2 times B1 is A2, right? So the first result is A2. The next one, A1 times A1 times B1. Go back. A1 times A1 is A1. And then A1 times B1 is B1. Go back. We put B1 there. What about A1 times B1 times B1? I just spoiled the fun. A1 times B1 is B1. B1 times B1 is A1. So that means this transition from A1 to B1 is allowed because inside the direct product, there is a totally symmetric representation. Yeah. So the totally symmetric representation tells us that this transition is allowed. Okay. Now this transition is not allowed from A1 to A2. It's not allowed. Okay. If you try it with the direct product, it will not be allowed. There will be no totally symmetric representation in the results. So it is a forbidden transition. Okay. So that's for water. And then I also put in for difluorobenzene. Okay. For difluorobenzene, there is another exception to the rule where rather than just looking at the electronic transition, we have to look at the vibronic selection rule. Okay. Where we have to add another the vibration into the direct product. Okay. It's all in the notes. Right, so other concepts in spectroscopy is something that I think you've done. Oscillator strength. Oscillator strength has to do with the value of R, yeah, the R and M. So in order to calculate oscillator strength, you have to calculate the value of R and M mathematically. Yeah. Chromophores, phosphorescence and fluorescence, something that you have done. This is a very good book. If you can find it on internet, it's an excellent book on spectroscopy. If you can buy it, then excellent. I bought one, it gets lost. I bought another one, lost. I don't know who took it. So now I'm using the electronic copy. So the electronic copy is available on the internet. So just find them. It's available. Yeah? But this is an excellent, excellent book. Okay, easy to understand. So this note that I gave you, the details is just one of the chapters or part of the chapter in the book. Okay. Okay, I'll just show you something else before we stop. Just discard this. Okay. Now I'm going to do some calculations in front of you. So here we're using Gaussian. Okay. So we want to calculate the water molecule. So we'll use oxygen. Oxygen. Okay. So this is going to be the input molecule. So we will this water molecule, and we'll prepare the calculation. I hope it's going to work. Okay. Okay, so we optimize the molecule and we are going to calculate the configuration interaction. So we use bigger BC set. All right. What else is there? Title. Okay, submit, save, test, go, save, submit. What is wrong here? What is wrong? Okay, never mind, there's something wrong here. I'll just read files that is already available. I've done the calculation yesterday. Open Dropbox. Dropbox. Okay. Desktop. Look at the log file. Okay. Right. No, should be a bond there. Anyhow, results. If you look at the UV visible spectrum of the water molecule, you have a few transitions there. This is the one that we did just now, A1 to B2 transition, which is the first. Sorry, it's this one. Sorry, this one. A1 to B2 transition there. Yeah. The A1 to A2 is somewhere here, but it's forbidden. And you also have this transition there. Okay. Now, if you look at the transitions, we can actually open the file. Oh, sorry. Let's open this file. All right, this is the log file of the UV visible spectrum. We just put it there. So can you see? Can you see the screen?
Yeah.
Yeah. Okay. So this is the log file. Now I'll just show you what I mean. Right. If you go down here, is it? There you go. Okay. So we start from here. Okay. Excitation energies, can you see? And oscillator strength up here. Excited state 1. All right. This is the B1 excited state. Right. So singlet B1, 1B1. So the transition which gives this energy, which is at 154, somewhere there, which is this one there. This transition here is this transition here, 154.69 nanometers. Yeah. The oscillator strength is not very good, but it's okay. Yeah, 0.0316. Okay. So this one is an allowed transition because it's A1 to B1. Okay, A1 to B1 is allowed. Now A1 to A2, this one, A1 to A2 down here, which is the next excited state. So A1 to A2 is not allowed. So the oscillator strength is 0. It is not allowed. So you don't see it here, right? The next one is A1 to A1. So A1, remember A1 is the ground state, right? So A1 to A1. So the next excited state is also of A1 symmetry. So it's an A1 to A1 transition. This is very allowed, and the oscillator strength is quite strong. So this one is the A1 to A1 at about 122.61 nanometers, which is this one. Yeah, this is a very strong transition. Okay. The next one, yeah, is A1 to B2. A1 to B2, also quite strong, 0.07, yeah, much stronger than the one above. So that is the transition there. And there's another one here and another one here. Yeah. So the results from the Gaussian calculation basically gives you the excited state transitions. So from A1 to B1, which is this one here, A1 to B1. Now you can see it's 5 to 6, 5 to 8, 5 to 9, right? So what are these actually? These are actually the molecular orbitals. Okay, the molecular orbitals. 5 to 6. What is 5? What is 6? I just have to go through this very quickly. So we can actually look at the molecular orbitals. Just load it. Desktop. Just load it. Okay, right. So we can actually see here. So for water molecule, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, right? The orbital number 5 is the HOMO, highest occupied molecular orbital. And you can see how it looks like. Hold on, visualize it. The HOMO. Okay, update. Right. So this is how the HOMO looks like. Let's make it big. This is how the HOMO looks like. Highest occupied molecular orbital. There you go. So one is positive, the other one is negative, right? So that's your number 5. So the transition, if you look at the listing again, the transition is actually from 5 to 6. 5 to 6. That's the first transition. It involves the A1 to B1 transition, involves electrons going from 5 to 6. How much electron is actually going from 5 to 6? The what do you call that? The Pekali, what is it in English? The multiplier, the constant is 0.5. This one basically gives you the probability lah. If you square it, it gives you the probability density of the transition. So it's 0.6 squared. It's about 0.4. Yeah, the probability density of this transition is about 0.4, right? So if you sum up all the transitions, it will equal to 1. Of course, the Gaussian only gives you the 4 main transitions, yeah. But if you sum them up, it's going to equal to 1, the square of it. Yeah? So there are also transitions from 5 to 8, yeah, which is at 0.01 probability density. Yeah, because you have to square this, right? So Gaussian gives you whether it is allowed or it's not allowed. A1 to B1, yes, it is allowed, and it also gives you the probabilistic numbers of the transitions from one molecular orbital to another molecular orbital. So this is a very interesting thing because this can be applied to a lot of different research lah. Yeah. So I'm sure over there di Pajajaran you also have something like this in terms of because there are a lot of free molecular orbital software as well. This Gaussian we bought like I don't know 15 years ago, you know. It's quite old. You don't have the money to buy the new license for the latest edition, but it doesn't. You don't really need the latest edition. What you have in order for you to understand the concepts of molecular spectroscopy, it is still sufficient. Yeah. Yeah. So basically, that's about it. Yeah. So we know that in molecular spectroscopy, electronic molecular spectroscopy, for big molecules, we use symmetry symbols, and we can work out the selection rules by doing direct product of symmetric representations. Yeah? And we can use software like Gaussian to actually see the nature of the electronic transition. Now, of course, the energy is not going to be the same. If you look at the real values, you just have to play around with the different methodologies to actually get the best value for that can be compared with the practical or the experimental value. But Gaussian basically gives you a good idea of how the transition occurs, where the electrons are redistributed. You can even look at the orbital pictures. Yeah, so it's a very useful software, which I think, yeah, I mean, undergraduates should have access to it. They should be able to use this software in order to do this kind of calculations. Saya rasa sampai di situ dahulu.
Terima kasih banyak, Prof. Sarif. Mungkin kalau ada question, mahasiswa, ada yang bertanya? Kita sudah lengkap dari electronic structure, dari atomic time symbol kepada molecular orbital, diatomic system gitu, kemudian sampai kepada transition ya di Gaussian. Di sini kita juga pakai Gaussian juga, Prof. Syarif. Jadi
Iya.
mungkin mahasiswa mungkin familiar juga dengan Gaussian.
Yes.
Gitu.
Nah, itu harus mereka harus diberikan peluang menggunakan Gaussian.
Ada pertanyaan?
Mungkin terlalu panjang nih, ada yang udah tidur ya.
Iya kayaknya ini menarik tadi Prof. Syarif, kayaknya sepertinya banyak overlap juga kita di mata kuliah kita gitu di itu.
Ya.
Kita juga ada tadi tanah besukan diagram juga kita ada gitu, belajar juga tadi yang Gaussian di computational chemistry, masuk juga yang itu apa namanya UV spektra ya di Gaussian gitu. Mungkin mahasiswa bisa disambung-sambungkan gitu ya, mulai dari orbital molekul ke electronic structure, electronic spectroscopy sampai ke aplikasi.
Karena kalau diajar mengenai molekul orbital hanya dengan teori quantum mechanics ya, itu akhirnya pelajar-pelajar itu tidak mendapat itu ya bagaimana ya? Experience tuh kita.
Iya.
Tapi kalau disatukan dengan spektroskopi ya lebih baik.
Iya. Sulit imajinasinya gitu ya, karena itu.
Ya gitu. Ya.
Ya alhamdulillah Pak Prof. Syarif sudah menggambarkan dari atomik sampai ke diatomik sampai ke aplikasinya lah di computational yang bisa kita lihat juga di apa namanya transitionnya dari HOMO ke LUMO, dari orbital ke berapa sampai ke orbital berapa gitu ya. Jadi bisa terlihat di situ semuanya, dan itu yang digambarkan dalam persamaan-persamaan yang ada tadi di awal gitu ya, Prof. Syarif gitu ya.
Ya.
Ya. Tidak ada pertanyaan, mungkin karena ini sudah jam hampir zuhur di sini, Prof. Syarif. Jadi makasih banyak Prof. Syarif atas kuliahnya yang sangat komprehensif. Mungkin kita perlu nanti ada sambungannya lagi dalam bentuk yang lain, karena ini menarik gitu bagi kami untuk bisa.
Ya bisa insya Allah.
Kalau bisa kita ketemu di
Saya mungkin insya Allah akan ke sana dalam bulan 8.
Bulan 8.
Mungkin tengah bulan 8 sampai akhir bulan 8.
Mungkin akhir bulan 8, karena tengah bulan 8 belum ada mahasiswa, biasanya baru akhir bulan 8 baru ada mahasiswa gitu. Ya. Masih cuti kuliah. Ya, makasih banyak Prof. Syarif, jazakallah khair. Mudah-mudahan ini bisa kita lanjutkan lagi dengan bentuk yang lain, dan sekali bisa kita lihat banyak yang theoretical itu melandasi bagaimana aspek-aspek yang ada di teman-teman di organik kerjakan, baik itu spektroskopi ataupun hal-hal lain yang terkait dengan sifat-sifat yang itu kita pelajari secara matematis, kemudian muncul dalam bentuk spektranya yang itu diperlukan oleh teman-teman yang ada di organik dan yang lain-lainnya. Sekali lagi makasih banyak, dan pada rekan-rekan mahasiswa ini sangat penting ya, karena walaupun kita berat gitu ya, banyak teorinya sulit diimajinasikan, tapi dengan bantuan software kuantum tadi kita bisa melihat dari ini yang terjadi transisi dari orbital ke sini sehingga tadi yang E1 ke B1 gitu, jadi berapa lagi itu ada di sana di Gaussian, ada semua gitu ya Prof. Syarif gitu ya, sehingga bisa membantu kita untuk melihat itu semua ya. Sekali lagi makasih banyak, mudah-mudahan kita bisa bertemu di bulan Agustus dalam bentuk yang lain lagi. Dari saya sekian saja. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.
Dari Bu Yesi ada teman, Bu Yesi? Bu Atik ada?
Iya Pak. Nggak ada Pak, ini WFH.
Dari rumah ya?
Oke, assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Terima kasih Pak.